Electromagnetism rests on the Maxwell equations. They are given here using the nabla symbol. Nabla dot means divergence and nabla cross means curl. So we have nabla dot of the electric flux density is equal to the charge density. We have nabla dot of B is equal to 0 always. And we have nabla cross of the electric field strength is equal to the negative differential of the flux density of the magnetic field. And finally, nabla cross of the magnetic field strength is given by the current density plus the Maxwell addition, the time differentiation of the electric flux density d. In general, the Maxwell equations are time dependent. However, they simplify greatly because electric and magnetic fields decouple if the situation is static. Then all fields and also the charge and current densities are only functions of position r. The decoupling creates two sets of two fundamental equations, two postulated Maxwell equations of electrostatics, nabla dot d equals rho and nabla cross E equals 0, and two postulated Maxwell equations that define magnetostatics, namely nabla dot B is always 0, this equation is unchanged from the most general form, and nabla cross H is equal to the current density J. It is thus convenient and pedagogically fruitful to discuss electrostatics and magnetostatics separately. Starting with electrostatics, and since nabla cross E is always 0, it's common to consider the first of those two equations, nabla dot D equals charge density, first. The mathematical meaning of this first postulate can be expressed in words as a static charge distribution, a given charge density, creates a divergent electrostatic field D. Looking at the first Maxwell equation of electrostatics, nabla dot D equals rho, or divergence D equals charge density, the obvious question is, how is charge density related to the total charge in a section of space? This can be decided by integrating the charge density over this section of space, according to total charge Q is equal to the integral, in this case indicated as a volume integral, over the volume charge density rho v. In this case, the charge density is expressed in Cartesian coordinates x, y, and z. Depending on the symmetry of the problem, it may, however, convenient in other cases to use either cylindrical coordinates or spherical coordinates. This example shows how a charge density integration is carried out in Cartesian coordinates. A cube sits in the xy plane and the cube has a side length of 2 meters. Inside the cube are charges. The distribution of those charges is given by the charge density, that is a function of position r. Specifically, the charge density rho v is equal to x times y squared times e to the power of minus 2z, and it's given in units of millicoulomb per cubic meters. Since the charge density increases linearly with x and quadratically with y, but decreases exponentially with respect to z, there is a concentration of charges in the right-hand bottom corner of the cube. The integration is expressed at the bottom of the slide in its three components x, y, and z. It does not use the formal mathematical convention of notation, but readily assumes that in electromagnetism, functions are such that integrations can be swapped. In carrying out integrations like this, it is important to always be aware of the units of the integral. That's why the unit millicoulombs per cubic meters is written on the right of the integral. The integration is carried out in 3 steps, starting with the z integration. The general integral of the function e to the power of minus 2z can be guessed as minus 1/2 times e to the power of minus 2z. The specific integral is therefore x times y squared times minus 1/2 e to the power of minus 2z, with the limits 2 meters and 0. The definite result of the z integration can be pulled in front of the integral as minus 1/2 in brackets e to the power of minus 4 minus 1, bracket close. The integral of the y integration is 1/3 y to the power of 3. Substituting with the limits 2 and 0 gives 8/3. Finally, the integral of x is 1/2 times x to the power of 2. Carrying this out and combining with the other results gives a total charge in the cube of 2.62 millicoulomb. This next problem is very similar, although it's in 2 dimensions. In this case, a square plate is placed centrally on the origin. The plate has a diameter of 6 meters and the surface charge distribution is given by 4 times y to the power of 2 microcoulombs on meter squared. Since the charge density is independent of x and is proportional to y squared, there will be concentrations of positive charges near the upper and lower edge of the square as drawn here, with y positions of 3 and -3 meters. The integration is straightforward. The y integral is 4/3 times y to the power of 3 and the x integral is x. Substituting with the limits 3 meters and -3 meters in each case gives the total surface charge on this square plate of 432 microcoulomb. In this problem, a circular disk is charged, with the concentration of charges decreasing with increasing radius. Since a disk has cylindrical symmetry, it is convenient to carry out the integration using cylindrical coordinates r and phi. Since the charge density is independent of phi, the phi integration gives 2 pi. This can be pulled out of the integral together with the constant factor rho naught. The integral of the r dependence is minus r times e to the power of minus r minus e to the power of minus r. This can be demonstrated by differentiating the integral with respect to r, which gives minus e to the power of minus r plus r times e to the power of minus r plus e to the power of minus r. The first and the last term cancel with each other so that we obtain r times e to the power of minus r. Since no specific dimensions are given in the problem, the result of the charge density integration is equal to 2 pi rho naught times 1 minus bracket 1 plus a bracket close times e to the power of minus a bracket close. Shown here are the volume elements for cylindrical and spherical coordinates. In the case of cylindrical coordinates, dv equals r, dr, d phi, dz. That's illustrated underneath, with the z-axis coming out of the plane. The equivalent volume element for spherical coordinates equals r squared times sine theta, dr, d theta, d phi. The definition of the parameters is illustrated below. One should be aware that not every author follows the same parameter definitions for coordinate systems. Sometimes r is replaced by rho, and also phi and theta are often swapped. It is therefore important in problem solving to, at the beginning of the solution, define the coordinate system and the parameters that are used. Apart from volume and surface charge densities, line charge densities can be defined as the ratio of charge per length. The unit of line charge density is thus coulomb per meter. A nice example for this is a nylon fishing line that is charged along its length. The electric charge might increase with length, for example according to rho L equal to Z. What is the total charge in this case for the section that goes from Z equals 0 to 10 centimeters? The integral is shown at the bottom and gives the result of 10 microcoulomb. An electrophorus is a simple electrical instrument with which charge distributions and the fields generated by them can be explored. An electrophorus or charge carrier is one of the oldest electrical instruments. Combining a conductor, 2 insulators, and an intermittent connection to Earth, charges can be transferred from Earth to the carrier and vice versa. The charging and discharging involves 4 steps that are illustrated here. Initially, a perspex plate, which is a good insulator or a good dielectric, is charged triboelectrically by fiercely rubbing it with a cloth. If electrons are removed, the dielectric plate remains positively charged. We have a relatively uniform positive charge distribution on this insulator. The positive charges cannot move away because they are on an insulator. In a second step, a conductor is placed right on top of the dielectric. This is the actual electrophorus. It can be handled with an insulating handle. The charged plate, the dielectric plate, induces charge separation in the electrophorus, so that we now have a layer of positive charges in the dielectric perspex, above that a layer of negative charges in the electrophorus, and above that another layer of positive charges due to the charge separation. Connecting now in a third step the top of the electrophorus plate with Earth, negative charges can travel from Earth to the top, compensating the positive charges in the layer at the top of the electrophorus. We therefore now have a surplus of negative electric charges in the metallic conducting plate of the electrophorus. Finally, if we now lift the electrophorus, we can transport this surplus of charge anywhere. It can also be discharged via a spark so that the surplus of charges returns back to Earth. Neglecting some residual conductivity of air due to moisture, this process can be repeated indefinitely, since the dielectric, the perspex plate, stays positively charged forever. The electrophorus allows us to create charge distributions of our own and play with them. It is interesting to work out how the total charge can be calculated for distributions like that. Let's consider the insulating perspex plate that carries the electrophorus. If we rub this at one end, we might get a charge distribution as shown in this sketch and schematically graphed underneath. This distribution with most charges towards one corner of the plate is difficult to treat mathematically. Let's therefore assume we rub the plate right in its center. That should produce a charge distribution which we can approximate with an inverted parabola as shown on the right, which might have the functional form of 1 over a squared times rho naught times in brackets a squared minus r squared, whereby a is half the side length and r is the distance from the center of the coordinate system. What is the total charge q that we have created in the center of this perspex plate? We're starting our solution by writing down the integral for a surface integration over rho s in Cartesian coordinates x, y. Substituting with the charge density function that was just discussed, we obtain the integral at the bottom of this slide. In order to achieve this, the rule of Pythagoras was applied. Although this integration is now straightforward, it is somewhat convoluted and does not need to be discussed in detail. The 5 steps are shown here. The result is then that the total charge on this perspex plate is 4/3 times a squared times rho naught. We can convince ourselves that this is a correct result by checking the dimensions. Indeed, multiplying the surface charge density rho naught with a squared, a length squared, gives a total charge in units of Coulomb. The result appears to be correct. Another verification is that this total charge should be less, somewhat, than the charge that would be obtained if the surface charge density rho naught would be constant over the entire perspex square. The calculation right at the bottom shows that this is also the case. We can be confident that the result is correct. Once the electrophorus disk has been charged with, say, negative charge carriers, we want to know what the total charge is on the disk. This is not straightforward because the disk is a conductor and the charge carriers can move. They will repel each other until a static, stable configuration has been achieved. It's illustrated here. All charges are at the surface of the disk, and the interior of the disk is charge carrier free. We thus don't have a uniform charge distribution with constant volume charge density ρ. However, if we assume the thickness of the disk to be negligible, it is a good approximation. In contrast, on all surfaces of the disk, the surface charge density is constant. If we therefore calculate the total charge on the top surface and the total charge on the bottom surface, which should be equal, and add them together, we obtain the total charge on the disk. However, again, we have neglected the contribution from the edge. The first approach is detailed here. Because of the cylindrical geometry of the disk, cylindrical coordinates r, phi, and z are used. The charge density is constant. The volume differential is equal to r dr d phi dz, as indicated by the red arrow. After substituting for the charge density with the constant ρ naught, it is clear that the only variable parameter in the integral is r, from the volume element. Carrying out the integration in 3 steps gives the result as pi times d times ρ naught times r squared, whereby d is the thickness of the disk and r is its radius. This result is simply the volume of the disk multiplied with the constant charge density ρ naught. The second approach is shown here. In this case, a constant surface charge density ρs is assumed, and the total charge is then calculated as the surface integral over this charge density. Again, cylindrical geometry is used. The surface element is thus equal to r times dr d phi. Integrating from 0 to the radius capital R and phi from 0 to 2 pi gives a result of ρs times pi r squared. This is simply the constant charge density times the surface area of the disk. Applying this result to the electrophorus disk, we have to consider that in this case we have an upper surface and a bottom surface, so that the total charge Q on the electrophorus disk is twice ρs times pi r squared. Charge distributions are quantified using charge densities. The total charge associated with a charge distribution can be determined by integrating over the charge density. This integration has to consider the geometry of the problem. If the situation is spherical or cylindrical, the respective volume element has to be used.